Analytics, data analytics. I'm going to review for the next 20 minutes to half an hour on what our relatively new group has been doing. I'd like to introduce our team members. I'm Jeff Harris. I came out of retirement from the GSC to manage this project and conduct mineral potential mapping surveys. There's Eric Grunsky, who is our world leader in the geochemical analysis and also does a lot of mineral potential mapping. Haran Bienya, who now is a full-time employee for Metal Earth, is our GS expert and also does a lot of mineral potential mapping. All three of us are ex-GSC employees. I don't know if that's a good or a bad thing. And there's Heming Liu, who is also a research associate at Laurentian University. He's doing a lot of work on geochemistry and mineral potential mapping. And Mustafa Nagazeta is our 3D geophysics expert. Now, we hope more people will join in our group. We're especially interested in the transit leaders who we could use their expertise on geological modeling and exploration vectors. So the objectives of our project is the overall objective is fertile versus non-fertile greenstone belts. Why does this occur? What are the reasons for this occurring? And what we're trying to do is create 2D and 3D mineral potential models or mineral potential maps from the collected data for each transect using machine learning languages. So what is a mineral potential map? Well, a map which shows the potential measured on an objective or subjective scale of a given mineral commodity over a given geographic area using a variety of georeferenced geoscience data. That's a bit of a mouthful. It should include a measure of uncertainty, and we'll show you that in our talk. So in the literature, you have mineral potential means the same thing as favorability, prospectivity, suitability, a mineral potential map. However, we're not indicating any estimates of tonnage or grade similar to what the USGS does, although we could look at that down the line. Here's just a schematic or flow chart of our modeling process. We start with an exploration model, so mesothermal, orogenic gold, VMS, whatever. And from that, we establish vectors to mineralization. And we've heard a lot about that in the last 4 days or so. And from that allows us to select evidence or predictor maps from our GS database that we can use for modeling. And these can be in binary form, multi-class, or continuous surface maps. And then we choose a modeling method, whether it's data or knowledge driven or a combination. In our case, which I'll be presenting today, we're using a data-driven algorithm known as random forest. And then assignment of the weights, that depends on the method we're using. For random forest, it's automatically derived. And then we come up with some prospectivity or potential map. The exploration model is the most important part of the modeling process, and this is why we need the transit leaders' help in this. It governs what evidence or predictor maps will be used in the modeling process. So it's obviously the key part of the whole thing. Our models are based on knowledge, experience, and empirical evidence. And often our models are dynamic or volatile, or exceptions to the model as more data becomes available or more science is done to indicate what are important vectors to mineralization. This is just a summary I put together back in the early 80s when I was working the SWAYZE Greenstone Belt with Kevin Heather and John Eyre. And this just shows you, on the left here, we're looking at the vectors to mineralization. And for example, QFPs were thought to be important in the SWAYZE for mobilizing gold, gold-containing fluids. So obviously what we want to do from our GIS database is extract QFP, quartz porphyries, from our database and use that as a predictor or indicator or evidence map. And we can do the same thing for high strain zones. We can extract data from the mapped geology that's already in existence, or we can interpret magnetic data for shear zones and faults, etc. And down the list, you can see that we're looking at lithology, structure, alteration, and of course, geochemistry, which becomes very, very important. So the model we're the models we're producing, we use what's called a random forest, which is a relatively new ensemble classifier. We start by creating a series of forests, or each tree, which creates then a forest, i.e. that's why we name it random forest. So the number of trees is specified by the geologist. We can have as many trees as we like, but I'll show you a way of how we decide how many trees we should have. We have a set of training data. All machine learning languages that are data-driven require training data. And this will be our mineral prospects or mineral occurrences or mines. And what we do for each tree here is we take 2/3 of our training sample and we use that to put down our tree and make our classified map at the end. And our map that we're classifying is either predictive or non-predictive zones. It's a binary map. And we leave out 1/3 of our prospects for validation. So we put these prospects down our tree, and we can establish what's known as an out-of-bag error. And that tells us how well our classification algorithm is working. The second degree of randomness comes from, we don't put all our evidence maps or predictor maps down each tree. We take a random sampling of our predictor maps. And usually in the case that I'm using, we take the square root of the number of predictor elements we have, and we put them randomly down the trees. And what this produces is a model, if you like, for each tree. And then what we do is, to reduce the variance of our models, is we combine all our decision trees together, take a majority vote. So on a pixel basis, if that pixel says this was predicted as a prospective zone, then it becomes a prospective zone. If it wasn't predicted as a prospective zone, then it becomes a non-prospective zone. So that's the way random forest works generally. It's a bit more complicated than I've described, but I think that description is probably okay for now. And we produce two types of maps, a classification map, and we produce a probability map, which is really our strength of membership for each class. And I'll show you that shortly. So here's some example of what we've done for Ruan Miranda for VMS to date. And this is all Paran Biene's work, who's our GS expert. So credit goes to Paran for this. Here's the geology. I won't go into the geology. We all know the geology. Greenstone belts dominated here by sedimentary terrain and granite terrain. This is where the area that we are modeling, or that Paran is modeling. So we're using various types of maps: a lithological map, proximity lithological contacts, proximity to regional faults, magnetic data, our 3D resistivity and susceptibility data, and of course our lithogeochemistry. These are the evidence maps, if you like, that we're feeding into our model. So here's just an example of proximity to faults. What we've plotted here, or what Paran's plotted here, is the VMS deposits in relation to our faults. And here's a buffer of 1 kilometer around our faults. Now that 1 kilometer is up for discussion. I was just talking to Jordi today, and she mentioned that she could see signs of alteration up towards 500 meters. So maybe that buffer should, instead of 1 kilometer, should be 500 meters. Here's an example of what we do with contacts. This is the general geology. And we buffer, in this case, we buffered 100 meters around each contact. So these are two examples of maps, evidence maps that we put into our modeling. We're using resistivity and conductivity and density. And this is the work of Mustafa. And this is just a cluster map that shows here zones of high resistivity, high susceptibility, high resistivity, low susceptibility, and so on. So this is work that Mustafa has done. And I believe that this is a depth from 0 to 750 meters. So we're looking essentially at the surface, but we're trying to incorporate other depth levels into our modeling as well. This is our magnetic data, where we're looking at magnetic anomalies. Again, this is an example of maps we produce into our model. Now, this is something that Mustafa's put together, kind of a neat model 3D. So you can look at the density, what's happening here. This is the density. This is now we're looking at resistivity. Now we're looking at susceptibility. And the next thing we'll be looking at are the clusters that he's done. And you can see the cluster number 1, low density, low resistivity, high susceptibility. So what we're trying to do here is make depth maps and put each depth map in turn into our models. So this is the way of incorporating some 3D information. And we're still doing that sort of analysis as we speak. So that's a pretty neat cartoon that Mustafa has put together. Of course, we use lithogeochemical samples. This is a dense database here in the greenstone belts, far less dense in the sediments and granitoid terrains. Some of the issues we're looking at is what to do with censored data, because a lot of this is historic data, and a lot of the data we're finding is below detection limits. So what do we do with that? And Eric is our expert on this, and he's been advising on what to do. Both myself and Paran and Hemming. We're looking at the closure problem using centered log ratios. And then we're looking at indicator elements. And we determined this from IOGAS software, which has different models, VMS, orogenic gold, etc. And these are the indicator minerals and pathfinder elements that is recommended by IOGAS. And we use, to interpolate our data, we use what's called inverse distance weighted. Now, interpolation of data can become problematic. Here we have a very dense network of sample points for the lithogeochemistry. But if you have a paucity of points, you can, if you contour that data, you can get completely false, meaningless patterns. So we got to be very careful when we're presenting this geochemical data. So what we do is follow the IOGAS model and use very small zones of influence around each point to interpolate the data. And in this case, we used 1 kilometer data, 1 kilometer search radius, if you like. And these are the maps that Paran has produced, univariate maps for our indicator and pathfinder elements. And you can see the similarities in some cases between our maps here. So we're starting with lead and going to elastite here. So each of these we could put into our model. We also use principal components, and Eric, as I said, is a world expert on principal component analysis. So if you're there, Eric, please chime in if I screw things up here. It's a data reduction technique. We can take n-dimensional data, such as geochemistry commonly is, and reduce it to a fewer number of variables or components that describe most of the variance of the data set. We can also do biplots, and we saw some of this yesterday, where we can plot PCA 2 or component 2 against component 1, and we can look at the influences of each of our input elements. For example, looking at principal component 2, we get what's looking like a gold and silver component. So we can import that into our maps. Again, as I see here, instead of looking at the individual univariate analysis, we can in fact look at the principal components, because each principal component we can name as, for example, as I said, this one is a gold silver component here. These are just summary of the maps we've already talked about that we've put into our models. Now, with random forest and any data-driven machine language, we need a set of training areas. And in this case, Paran has extracted 83 VMS occurrences over the area shown in red dots. But also what we need for random forest to work properly is a set of random points that reflect non-mineralized points. How we do this is we're still investigating best methods. And there's a lot in the literature will tell us that to deal with this research. But here's our set of random points, 83 random points that we have over our area. So this is our training data set. So here's our first model that Paran has produced univariate geochemical data, and our second model using multivariate geochemical data. You can see they're quite similar, but there are differences. Notice that here is low potential because we didn't contour data because we had no points here. So you got to be careful about that. Most of our points, as you recall, are up in the greenstone belt area. So that's why we have a nice looking map, and you can see the effect of the 1 kilometer search radius. So looking at some of the statistics, what we're looking at here is the number of trees that Paran produced, 1,000, and what's termed as the out-of-bag accuracy. If you recall that each tree is built on 2/3 of the population of our mineral occurrences, and 1/3 is left out for sticking down our tree and assessing our prediction accuracy. And this is exactly what this curve is plotting here. And you can see quite nicely that it stabilizes at about 78% here. Our out-of-bag accuracy is 78%. So this is telling us that we don't need as many trees as 1,000. We could probably get away with 600 trees or maybe 500 trees. What we're seeing here is just in our high perspective zones, or prospective zones, our potential zones, which is labeled by 1, and our non-potential zones by 2, we can see 82 of our fine occurrences occur and are predicted well in our high probability zones, where only 1 falls in the non-perspective zone. Where we can see the case is a bit different for our random points because they are random. 7 occur in the prospective zones, only 70 and 76 occur in the non-prospective zones. And this leads to confusion matrix analysis, and this results in about a 95% accuracy of classification of our VMS occurrences. Again, what is nice about random forest is that we can rank the variables in importance of prediction, if you like. And this is done by using what's called the Gini index that's calculated for each tree. And it's basically a measure of information gain or information lost. And you can see in this particular case, which we just show for our multivariate model, where we use PCA, these are the evidence maps we put into our model. For example, PC1 to PC6, lithology, faults, cluster map, magnetics, and lithological contact. We can see that the PCA2, which is that gold map, gold and silver map, has a fairly high predictive power. This is a normalized value. The higher the number, the more predictive power each evidence map has. And the normalized value is just where we take the raw data and divide it by the standard deviation. So you can see the PCA2 is quite predictive. More gold occurrences occur on that pattern, if you like, than we'd speak from random. And we also, our faults are buffered around 1 kilometer. They're also very predictive, and so on. Notice our cluster map in this particular case is not very predictive at all, but that has changed with other models we have been undertaking. So another way we can look at how well we've done is through efficiency of classification curves, or success rate of classification. And what we're doing here is plotting area of each of our potential maps. So this is the high potential here, medium potential here, and lower potential here. And what we're plotting is the cumulative frequency of mines or occurrences. In this case, there was 83, as I mentioned, that Paran took from our GS database. And if we get a banana-shaped curve like this, this is meaning our model is performing pretty well. For example, almost 100% of our occurrences in both models are predicted in less than 20% of our area. So you can see how it's decreasing our area of search appreciably. And this is just a detail where we look at the 2 models, the univariate geochemical analysis where we use the individual elements, and the multivariate model where we use the principal components. And you can see that the model using the principal components is a slightly better performer, because roughly 80% of the VMS occurrences are predicted in about 5% of the area, where in this case for the univariate analysis, we're predicting in about 8% of the area. So these efficiency curves are very, very useful. On to Sturgeon Lake. This is a very preliminary model that we have. I've got the model here. So I should say that the warmer colors are higher potential zones. The cooler colors are lower potential. And what I've done here is overlay the gold occurrences. We're looking at orogenic gold now instead of VMS. Again, the same statistics, a little over 80% out of bag accuracy, which is pretty good. 90% classification accuracy. And if we look at, I'll just move this out of the way. Here's what we put into our model, for example, a detailed rock map, regional rock unit, mag high strain zones, gravity, rock gravity, etc. You can see what we've put in here, including our 3D data here, 0 to 750 meters, a surface model. And here again are our predictors. And you can see in this case, the gravity really is a strong, strong predictor in this particular model, followed by the 3D resistivity map down to 750 meters, also a very strong predictor. So this is very interesting. And here's our efficiency of classification curve. Again, you can see what generally we like is more of a banana shape that looks like that, but this is done okay. About 100% of the deposits are predicted in our model in less than 35% of our area. Looking at just hot off the press, looking at the southern SWAYZE, which is dear to my heart because I helped map in that area years ago with Kevin Heather from the GSC and John Eyre. And what I'm looking at here now is a model based on just the mines and producers and past producers, which is a total of 13. And here you can see this is a pretty robust model, and we put lots of evidence maps or predictor maps into our equation, including alteration indices, fault contacts, our 3D data again. And this is the result we're getting around 92.3% accuracy. And here are our curves for the mines in blue. And you can see almost 95% of the mines are predicted in less than 50% of the area. So these are the mines, and they're plotted again on our map here. Here's when we just look at the occurrences. So this is 28 occurrences, and again, we've got the occurrences plotted on the map. Again, just to remind you that the warmer colors are high potential, the cooler colors are low potential, and generally in areas where we don't have very good data, specifically geochemical data. But notice this is not as performing as well if we look at the classification curve, because if we're close to 95%, we can predict in 55% of the area, which is much poorer performing than some of the others. So one may ask yourself, well, can the predictor map based on the mines predict the occurrences and vice versa? Well, here's the result of that. And really what it's telling us is the random forest mine prediction map does not predict the OU occurrences, the gold occurrences very well, whereas the RF occurrence prediction map predicts the mines reasonably well. So that's that curve here. And when we have a straight line in this curve, that means there's really no predictive power. It's not much greater than random prediction. So one idea we thought in terms of the overall goal of Metal Earth in looking at fertile versus non-fertile belts, we've plotted here some of our models here, Noranda, univariate geochemical analysis, Noranda, looking at multivariate, Larder Lake, which I haven't presented at all because Hemming, one of my colleagues, will be presenting that shortly, and Sturgeon Lake. So this is the rank as established by the random forest for the best predictors for each model. And you can see, read across and get an idea of what are the best predictors. So the idea here really is, can we compare across transects in terms of the best predictors, the highest predictors? Can that tell us anything about geologic process that's happening that can shed some light on fertile versus non-fertile belts? So we haven't done any thinking about this at this point, but this is just an idea we're coming up with, the team is coming up with. So in summary and conclusions, we would like to continue to build our team, invite more members in to work with us and utilize your geological expertise, and especially defining the exploration models. We've worked on 4 transects to date. Some of them are only preliminary models, but obviously we're going to add the other transects. I'm especially interested in the new Abitibi compilation coming our way, hopefully, and I'd love to incorporate that in some of our models. In fact, why not create a model for the entire Abitibi belt? and that would be something we could do. We're still investigating through Mustafa's help how to integrate our 3D geophysical data. We're looking at depth slices now and putting each depth slice into our model. So we have a surface model, a mid-surface model, and a deep model. And we're trying out that and see how well that works. And so far, preliminary results seem to indicating that that works well. In fact, work that Paran has just done is indicating that's working well. The other thing we have to think about as data analytics is how we're going to release this data. Are we going to release the raw data and derived products? And there's always political considerations there, like who owns the data, et cetera, et cetera. We're looking at obviously published papers. A lot of the people who I'm working with are fairly young and have to publish research papers. So we're looking at that. Machine learning issues is some of the things we're investigating is if the number of deposits are too few, how's that affecting random forest? And do we have to go to a knowledge-based system, for example? How best to create random points, as I mentioned earlier. And also to stabilize the variance of our models, we're looking at what's called repetition, repeating the model, say example, 10 times, and then taking the average. Processing of the geochemical data, Eric's very, very knowledgeable about the effects of closure. So that becomes close to our heart in looking at that. And interpolation is close to my heart because I know in some cases, if we interpolate with the paucity of points or low density of points, our patterns can be quite meaningless. So I'd like to thank you. And I put my email on this slide and I'd love to hear responses from people and we'll go from there. Okay, thank you very much.